This is the Mollier building, the oldest building of TU Dresden, here on the central campus of the Technische Universität in Dresden, the original machine laboratory of TU here in Dresden. The building has been named after Richard Mollier, well known to everybody in mechanical engineering from the Mollier diagrams. Let's have a look inside. The machine laboratory is from its beginning a place of experiments, and thus it's also a place where measuring technology has a major importance. By the way, my name is Stefan Odenbach, and I'm here at the Department of Mechanical Engineering, Professor for Magnetofluid Dynamics. This is a special kind of fluid mechanics where we deal with magnetically controllable liquids. Measuring and automation technology is of severe importance for our everyday life. As we can see here with a simple example of a thermostatic radiator valve. Aside such tasks in everyday life, measuring and automation technology has obviously great importance for science, ranging from gas turbine investigations, as we have it here, with a rotor equipped with hundreds of probes to measure temperature and pressure, towards microstructure investigations with microtomography, as we can see here. Microtomography is a tool that allows us to get an insight into the inner structure of materials, for example, or to look into processes on a micrometer scale using X-ray images which are combined by complex algorithms. Experiments and fluids. These are the ingredients of our scientific work here in the machine laboratory. And thus, I would like to take you to a journey through the world of complex fluids. And for the upcoming week, we will ask you to do some experiments with fluids which behave a bit different from what we normally know from a normal liquid. If we talk about complex fluids and their behavior, the science behind is usually called rheology. That comes from Greek and means the science of flow. And thus, if we want to look a bit deeper into this rheology, we should first of all answer the question what it means if we say a fluid flows. To get a deeper insight into this question, we should go back to Newton's definition of viscosity of a liquid. Let's assume that we have a liquid in between two rigid walls. One of the walls, the lower one here in the picture, is at rest, while the other one is moved by a force and moves with a velocity v0. Within the fluid, as we know, we will get a linear velocity profile starting at velocity 0 at the lower boundary and growing linearly to the upper boundary to v0. And Newton defined the dynamic viscosity as a proportionality factor between the force which is acting on the upper plate and the velocity that we can reach in a certain fluid. If we look a bit deeper to that, we see that the stress, that is the force that we have to exert for a certain surface of these plates, is proportional to the velocity gradient in the fluid that we can achieve. And again, the proportionality factor is a viscosity. That does not answer at the moment the question what it means that a fluid flows. Therefore, we have to have a look inside the fluid And we look on a volume element of the liquid, that is a small portion of the liquid which is now moving under the action of this external force. This fluid volume element will deform over time as long as the external force acts on the fluid. And this permanent deformation, ongoing in time, is what we call flowing of a fluid. In this case, the viscosity is the resistance of the fluid against this ongoing deformation. To get this resistance against deformation in a liquid a bit more visible, I've brought a couple of different liquids with me, and we will make a simple experiment just to see what happens. And we start with water. We all know what happens if I give a droplet of water to this dish here. The droplet will run down the dish. And you see it flows quickly downwards, and it deforms during this flow behavior. This is a very low viscous liquid, and we will now change to a liquid with higher viscosity. I've brought a silicone oil with me, which has a viscosity which is about 10,000 times higher than the viscosity of water. And if I place a droplet of this silicone oil up here, you can see the droplet, simply due to the fact that it flows much slower than the water droplet before. You see the deformation during time, and the fluid flows down the dish. And now we come back to a liquid that you all know from everyday's life, a toothpaste. This is also a liquid. And we will see what happens if we give a bit of toothpaste on this dish. That is a toothpaste, and nothing happens. The same stress is acting on this fluid as on the water or on the silicone oil before, but the paste does not go down. That is a completely different behavior. And fluid behavior can become even more complicated. This liquid here, which we will discuss a bit more in detail later on, shows quite a different behavior. You can see that if you look on the stream which is going down, which is much thicker than you would expect that, and it seems that it slows down while pouring into the second beaker. It's quite difficult to stop flowing at that point. And if you try to stir this fluid, you will see that it reacts. It hardens out. That is, with increasing mechanical load, this fluid becomes more viscous. And if I try to get the spoon out a little bit faster, you will see that the whole glass comes with me. And finally, the green one here. This is obviously very viscous. At the moment, you can't see that it flows at all, but I can deform it. And if I make a ball of it, this ball will jump. And if I place it down and give him a bit of time, it will flow again. Thus we have here a combination of viscous and elastic properties, a viscoelastic fluid. Aside such fluids which change their viscosity due to the action of mechanical forces, we have also liquids which can be controlled by external stimuli. For example, by magnetic fields, like it is seen here with this ferrofluid, which reacts to the action of an external magnetic field, and which can be controlled concerning its flow, like it is seen here, or its viscosity due to a very simple external stimulus. In these fluids, small magnetic particles form structures, like for example chains, and this gives rise to an increase in viscosity. If we have micron-sized particles in such a suspension, we get a magnetorheological fluid. Such fluids exert yield stress if a magnetic field is applied. We can see that here if we let the sphere drop into the fluid. The fluid is rigid and stops the sphere. And if I remove the magnetic field by removing the magnet below, you see immediate that the sphere sinks inside the fluid. We've seen now quite different behavior of these different liquids. And only those fluids for which viscosity does not depend on the mechanical load, that is, for example, on the velocity of steering that we try to apply, are Newtonian liquids. The question that we have to ask now is how rheology can describe and quantify the behavior of these liquids. The normal way to do that is to use a flow curve. A flow curve is a relation between the stress applied to the fluid and the shear rate, that is a velocity gradient that can be established by the given mechanical load. For a Newtonian liquid, this flow curve is a linear relation starting for zero stress at vanishing shear rate and increasing with a constant viscosity with a constant slope. The slope, as mentioned, is a viscosity in these diagrams. For the other liquids, the flow curves are nonlinear. If we look to a fluid, like we've seen it in the experiment before, the fluid that showed this extreme increase of viscosity with increasing mechanical load, we get a flow curve like this. The shear rate rises less and less if I increase the mechanical load. These are so-called shear thickening fluids, and you find them quite often in nature and technology. For example, colloidal suspensions show such a behavior. Examples for that may be inks or lacs, which we often use in everyday life. The contrary of these shear thickening fluids are shear thinning fluids. For these fluids, the viscosity decreases with increasing mechanical load, and we see that in the flow curve with a decrease of the slope of the flow curve. Examples here are, for example, any kind of polymeric liquids. Any kind of shower gel, for example, shows shear thinning behavior. The third kind of fluid that we have seen are liquids with a yield stress, like the toothpaste or the magnetorheological fluids. In these fluids, I have to apply a stress which is larger than the yield stress to get a flow started. Below the yield stress, these fluids behave like an elastic solid. This very different behavior of the liquids enters our life at many points. Many kinds of cosmetics, of foods, or, as mentioned before, of colors and lacs show complex liquid behavior. And thus, the understanding of rheology is important for our technology. Moreover, fluids, like the magnetically controlled ones that we have seen before, give us the possibility to change the fluid's behavior by external stimuli, enabling us to use them as controlled parts of actuators, like, for example, dampers. Such actuators can, for example, be used in bigger automation systems, like you will hear later on about in the part of University of Stuttgart. We have seen now quite many fluids with a quite complex behavior. And as mentioned before, I would like to ask you for the next week to do a couple of experiments with such complex fluids, just to get an idea what can happen if we use a fluid for very normal processes which behaves different from water or other normal liquids we know. The first experiment we would like to do is something that you have seen before. This white liquid which hardens if you increase the velocity of stirring. To produce such a fluid, you simply need a little bit of starch and water. And you need a balance. Of course, a mixture of starch and water is quite important. Use 57 grams of starch and fill that up with water to 100 grams. Then you will get a liquid like the one that I have here. But you have to be patient when you try to stir that, because fast stirring will not work at all. If you have produced it, you can try how it reacts on stirring, and afterwards you should slowly dilute it by adding, let's say, in small steps, 2 milliliters of water per step, and you will see how the behavior of the liquid changes. The results of your experiment should be posted in the forum. The second experiment is as easy as the first one. You buy 2 simple syringes, and you need a little bit of water and a shower gel. First of all, you take water into the syringe and press it out. Make a video and look how the fluid looks like at the nozzle of the syringe. Afterwards, you take the shower gel for the same experiment and you compare both results. Just post images or videos of your experiments in the forum and try to think about what probably could happen. We will give an explanation at the end of the week. The last experiment that we will have a look on is one of the most spectacular effects in rheology, the so-called K effect, discovered by Alan Kay in 1963. He published this effect in a Nature paper, and the last sentence is, "I can't offer any explanation for this behavior." What you see here in the experiment is a liquid pouring down from the top into a small film of the same liquid. And as you can see, sometimes the liquid jumps out. The liquid that we use here is again a shower gel. And you should try to make experiments where the fluid jumps like it does here. If you are successful with this experiment, you can post the respective videos in the forum. Astonishingly, it took more than 40 years to find an explanation for this K effect, and at the end of the week, we'll have a short explanation even here.